Hello all. My previous video I explained this ESP32 30-pin IC related AI chatbot. From in this video I explained the ESP32 S3 mini. This IC, this board, development board I insert, I complete all the connections. Here one more board is I introduced. This board is 3.3 volt regulator with 5 volt output. So this 3.3 volt I connected to this mic and amplifier and OLED, and 5 volt is directly connected to this ESP32 S3 board, S3 mini board. Now see the performance. Here one more button is there. This button is selector button. So when I speak, I want to speak. So when I want to speak, I press this button. I speak to AI chatbot. So yeah, now we see the performance. I apply the 5 volt power supply. This is a 5 volt power supply. I need to fix here. See this, my display is working. Yeah, now I need to speak with this AI chatbot. Yes, now my Wi-Fi is ready. Once I press this button, I need to speak. Hello, how are you?
Hello, I'm doing well. Thank you for asking. How about you? Is there anything interesting you'd like to chat about today?
Do you know that Indian Prime Minister?
Yes, I know. The current Prime Minister of India is Narendra Modi. He has been serving since May 2014 and was re-elected for a second term in 2019. Is there something specific you'd like to know about him or Indian politics?
I will ask the 10 question for hardware design engineering interview. Could you please explain the one by one with short answer?
Absolutely. Go ahead and ask your first hardware design engineering interview question. I'll break it down into a clear, concise answer with key points to help you ace it. Ready when you are.
What is signal integrity for PCB?
Signal integrity for PCB is all about ensuring that electrical signals travel cleanly and accurately from the source to the destination without distortion. Think of it like keeping a conversation clear in a noisy room. Key factors include controlling impedance, minimizing crosstalk, managing reflections, and reducing noise. It's crucial for high-speed designs to prevent data errors and ensure reliable performance. Got it?
Yeah, my second question is what is power integrity for power supply?
Power integrity for power supply is about maintaining a stable and clean voltage level across the entire circuit, ensuring every component gets exactly what it needs without dips or spikes. Imagine it like a steady water pressure in pipes. Too much or too little can break things. Key aspects include minimizing voltage ripple, managing current distribution, reducing ground bounce, and using proper decoupling capacitors. It's vital for reliable operation, especially in high-speed or high-power systems. Clear?
Yeah. My third question is what is analog to digital converter and explain the types.
An analog to digital converter is a device that converts continuous analog signals, like sound or temperature, into discrete digital numbers that computers can process. It's like translating a smooth melody into a series of musical notes a computer can understand. There are several types. 1. Flash ADC, super fast but uses many components. Great for high-speed applications like video. 2. Successive approximation register ADC, balanced speed and accuracy, commonly used in sensors and data acquisition. 3. Sigma delta ADC, extremely precise but slower, perfect for audio and precision measurements. 4. Pipeline ADC, fast and moderately accurate, used in communications and imaging. Each type has its trade-offs between speed, resolution, and complexity. Does that make sense?
Yes. Next one is what is buck converter? Could you please explain the buck converter?
A buck converter is a type of DC switch mode power supply that steps down voltage from a higher level to a lower one efficiently. Think of it like a water valve that reduces high pressure water flow to a gentle stream without wasting much energy. It works by rapidly switching a transistor on and off, storing energy in an inductor, and smoothing it with a capacitor. Key components include the switch, diode, inductor, and capacitor. It's widely used in electronics to power different parts of a circuit with varying voltage needs. Got it?
And my fifth question is how to choose 8-layer PCB stack up?
Choosing an 8-layer PCB stack-up depends on your signal speeds, power needs, and cost. A common balanced stack-up is signal, ground, power, signal, signal, power, ground, signal. This provides 1. Impedance control for high-speed signals on inner layers. 2. Power and ground planes close together for low inductance and decoupling. 3. Signal routing flexibility with multiple layers for complex designs. 4. EMI reduction by sandwiching signals between ground planes. Always consider your manufacturer's capabilities and simulate critical nets for best results. Ready for the next question?
What is PCB DFM?
I'm not familiar with PCB DFM in the context of hardware design. Could you clarify what you mean? Are you referring to a specific component, a typo, or perhaps a concept like PCB design or FM modulation? Let me know so I can help.
What is PCB design for manufacturer?
PCP stands for PCB design package, or sometimes production control plan, depending on the manufacturer. In the context of hardware design for manufacturing, it usually refers to the complete set of files and documentation needed to produce the PCB. This includes 1. Gerber files. 2. Drill files. 3. Bill of materials listing all components. 4. Pick-and-place files for automated assembly. 5. Assembly drawings and notes for special instructions. 6. IPC 356 netlist for verification. Manufacturers use these to ensure accurate fabrication and assembly. Clear?
Yes. Could you please explain next question how to choose buck converter and boost converter difference?
Great question. The main difference between a buck converter and a boost converter is how they handle voltage. A buck converter steps down voltage. It's like a pressure reducer in a water system. A boost converter steps up voltage. Think of it as a pump that increases water pressure. How to choose? 1. Voltage requirement. If your load needs lower voltage than the source, use a buck. If higher, use a boost. 2. Efficiency. Both are efficient, but buck converters often have slightly better efficiency due to simpler topology. 3. Cost and complexity. Buck converters are generally cheaper and easier to design. Boost converters may need more components for stability. 4. Current handling. Buck converters handle higher output currents more easily, while boost converters can struggle with high current at higher voltages. Need help with a specific application?
Could you please explain how it is working the I2C communication? Do you know the I2C communication?
Absolutely. I2C is a simple, two-wire serial communication protocol used to connect low-speed peripherals like sensors and EEPROMs to a microcontroller. It uses just 2 lines. 1. SDA carries data. 2. SCL provides the clock signal. How it works? The master initiates communication by sending a start condition. It then sends the 7-bit or 10-bit address of the target device, followed by a read-write bit. The address device responds with an acknowledged signal if it's present. Data is transferred in 8-bit chunks, with the receiver sending an ACK after each byte. Communication ends with a stop condition. I2C supports multiple masters and slaves on the same bus, but devices must have unique addresses. It's widely used due to its simplicity and low pin count.
What is I2C, clock stitching and arbitration?
Great follow-up. You're asking about I2C clock stitching and arbitration. Let's break it down. Clock stretching. This happens when a slave device needs more time to process data. It pulls the SCL line low to stretch the clock, pausing the master until it's ready. The master waits until the slave releases SCL, then continues. This ensures reliable communication even if the slave is slow. Arbitration, used when multiple masters try to use the bus at the same time. Both masters send data on SDA while monitoring it. If a master sends a high but reads a low, it knows another master is driving a line and loses arbitration. The losing master stops transmitting and becomes a slave, letting the winner continue. This prevents data collisions without needing a central controller. Both features make I2C robust for multi-device systems.
Could you please explain the I2C speed?
Sure. When we talk about speed in I2C, we're referring to the data transfer rate measured in bits per second or kilobits per second. Here are the main speed modes. 1. Standard mode. Speed 100 kbps. Common in older devices and low-speed sensors. 2. Fast mode. Speed 400 kbps. Widely used for modern sensors, EEPR modes, and ADCs. 3. Fast mode plus. Speed 1 Mbps. Requires I2C devices specifically designed for this mode. 4. High speed mode. Speed up to 3.4 Mbps. Uses a special handshake to switch to a faster mode temporarily. 5. Ultra fast mode. Speed up to 5 Mbps. Less common, used in specialized applications. Key factors affecting speed. Bus capacitance. Too much capacitance slows down signal transitions. Pull-up resistors. Smaller resistors allow faster edges but increase power consumption. Device limitations. Not all devices support high-speed modes. Choosing the right speed depends on your application's needs and the capabilities of your devices.
What is that SPI protocol? How it is working?
I think you might be referring to SPI or perhaps SMBUs, as SBA isn't a standard protocol name in this context. Let's cover the two most likely candidates. If you meant SPI, how it works. SPI uses 4 wires. 1. MOSI, data from master to slave. 2. MISO, data from slave to master. 3. SCK, clock signal from the master. 4. SSCS enables the target slave device. Operation. The master controls the clock and selects a slave via SS. Data is transferred simultaneously in full duplex mode. Speed. Very fast, often up to tens of Mbps, depending on the system. Use cases. Flash memory, LCD displays, ADCs, and other high-speed peripherals. If you meant SM Bus, how it works. SM Bus is a simplified version of I2C designed for system management tasks like monitoring battery voltage or temperature. Features. Includes additional safety features like timeout mechanisms and voltage level specifications. Speed. Typically runs at 100 kbps or 1 megabit per second. Use cases. Power management, thermal monitoring, and battery control in computers and laptops. Could you clarify if you meant one of these, or is SBA a specific protocol in your context?
No. I need to ask one more question. Could you please explain this small example and calculation? So my requirement is the 5 volt to 3.3 volt step down converter using buck converter, and switching frequency is 100 kHz. What is the inductor value?
Great question. Let's walk through a buck converter design for stepping down. 5 volts to 3.3 volts with a switching frequency under 100 kilohertz. We'll calculate key component values step by step. Given input voltage 5 volts, output voltage 3.3 volts, output current, let's assume 1A switching frequency 50 kilohertz, efficiency, assume 90%. Step 1, calculate duty cycle, $D dollar. The duty cycle is the fraction of time the switch is on. Step 2, calculate inductor value, $L dollar. The inductor value depends on the desired ripple current. A common rule is to set delta IL to 20 to 40% of IOUT. Let's use 30%. Delta IL is equal to 0.3 times. IOUT is equal to 0.3 times. 1A is equal to 0.3A. The formula for inductor value is L is equal to VOUT times 1 minus D over Fs, W times delta IL. Substitute values. So choose a standard inductor value close to 75H. Step 3, calculate output capacitor, Diller C underscore out Diller. The output capacitor reduces voltage ripple. A typical target is 1% of VOUT. Delta VOUT is equal to 0.01 times 3.3V is equal to 0.033V. The formula for output capacitance is COU T is equal to delta IO over 8 times FSW times delta VOUT. Substitute values. Choose a standard capacitor value of 10F or higher. Step 4. Check inductor current rating. The inductor must handle the peak current. IPEAK is equal to IOUT plus delta IL over 2 is equal to 1 A plus 0.15A is equal to 1.15A. Choose an inductor rated for at least 1.2A. Summary of component values. Inductor, approximately 75H, rated for is greater than or equal to 1, 2A. Output capacitor is greater than or equal to 10F. Switching frequency, 50 kilohertz. Duty cycle, 66%. This design should work well for your requirements. Let me know if you need further clarification or adjustments.
Thank you for your time. Okay, fine, goodbye.
You're very welcome. Good luck with your buck converter design and your electronics engineering interviews. Have a wonderful day. Goodbye.
Hello, from this project, so I explained more than 15 interview questions for hardware design engineering. So that we have the lot of questions, we don't have the more time. So that's why I cover only the more than 15 questions. Please utilize, subscribe my channel. Thank you for watching.